Welcome to Sleepy Stories, a place where you can learn about the universe at an easy pace. The goal is simple: to understand how nature works while allowing your body to rest. If sleep doesn't come right away, that's fine. The mind can stay curious while the body relaxes. If you enjoy these quiet lessons, a like or a subscription helps us keep creating more nights of calm science. Tonight's topic is the life of a star. Every star you see began inside a cloud of gas and dust. Astronomers call these regions molecular clouds, or stellar nurseries. They are made mostly of hydrogen molecules with smaller amounts of helium, carbon, oxygen, and silicon. These clouds are extremely cold, around -250 degrees Celsius, so atoms move slowly and stick together. The clouds are not uniform. Some areas are slightly denser than others, and over time, gravity makes those denser regions grow. When gravity pulls gas inward, the pressure and temperature in the center begin to rise. The material collapses into a roughly spherical shape. This marks the formation of a protostar, the very first stage of a star's life. Around it, a disk of gas and dust forms because of rotation. The rotation is not random. It comes from the conservation of angular momentum. As the cloud contracts, it spins faster, just as an ice skater spins faster when pulling in their arms. Inside this forming system, several physical processes take place. The infalling gas releases gravitational potential energy, which turns into heat. The core becomes hot and dense, but fusion, the process that powers a star, has not yet started. At this stage, the light we see is not produced by nuclear reactions, but by the conversion of gravitational energy into radiation. The protostar shines mainly in the infrared, which is why telescopes like James Webb are used to observe these hidden objects through their dusty envelopes. Material continues to fall inward, while jets of gas shoot out along the rotation axis, clearing some of the surrounding space. These bipolar outflows are a sign that the forming star is stabilizing. The disk around it will eventually cool and condense into solid particles, tiny mineral grains that can later build planets. This early environment contains all the ingredients for a future solar system, though at this stage, everything is still chaotic. The protostar stage can last millions of years. During that time, the central temperature slowly climbs. Hydrogen atoms collide more often as density increases. When the core temperature reaches about 15 million degrees, hydrogen nuclei, protons, move fast enough to overcome their electrical repulsion and start to fuse into helium. This moment marks the beginning of nuclear fusion. Fusion changes everything. The outward pressure from the energy it releases now balances the inward pull of gravity. The object stops collapsing and becomes a stable main-sequence star. Astronomers call this balance hydrostatic equilibrium, the state in which most stars spend the majority of their lives. From the outside, a newborn star looks calm and steady, but inside, nuclear reactions occur at enormous rates. Each second, hundreds of millions of tons of hydrogen are converted into helium. The slight loss of mass becomes energy according to Einstein's equation E equals mc2 E equals mc2 E equals mc2. That energy moves outward through layers of hot plasma, eventually escaping as visible light. This light travels across space, sometimes for billions of years, before reaching eyes on Earth. When you look at the night sky, the faint points you see are the results of these stable fusion reactions. They are ongoing records of balance between two fundamental forces, gravity and pressure. The process that turns a cloud of cold gas into a shining star is one of the most important in astrophysics. It explains where the sun came from and how energy spreads through galaxies. Each step, from collapse to ignition, can be modeled using the same laws of physics that describe motion, heat, and light on Earth. What happens on cosmic scales is not mystical. It is the same set of principles that govern a flame, a turbine, or a heartbeat, only extended across vast distances. As you settle into rest, keep in mind that stars are not rare events. Our galaxy alone contains about 100 billion of them, each following this same sequence. The difference between them comes down mainly to mass. Heavier stars burn hotter and live shorter lives. Lighter ones burn cooler and live longer. The Sun sits comfortably in the middle, massive enough to shine for roughly 10 billion years, gentle enough to provide steady warmth to its planets. Understanding how stars form helps explain much more than light in the sky. The same process that fuses hydrogen also creates the heavier elements found in air, rock, and living tissue. Every carbon atom in your body was built inside a star. The universe recycles matter through these stellar generations. The life of a star is therefore not just an astronomical event, it is part of the story of everything that exists. For now, let your thoughts slow down with that idea. In the vast cold of space, gravity gathers simple gas until fusion begins. Out of silence, light appears. The universe's most fundamental act of creation continues quietly above us every night. After a star forms inside its dense cloud, gravity continues to shape everything around it. Gravity is the fundamental force responsible for turning loose gas into a compact, stable object. It is not sudden or violent, it works slowly, constantly, and without interruption. Every molecule of gas attracts every other molecule, creating an inward pull that grows stronger as matter gathers in one place. Inside the collapsing region of a molecular cloud, this pull starts to dominate over any outward motion. As the material falls inward, the pressure and temperature in the center rise. The heating is not caused by external energy but by compression. The atoms move faster as they are squeezed together, converting potential energy into thermal energy. This is the same principle that makes air warm when it is compressed in a pump or an engine cylinder. As collapse continues, the core of the forming star grows denser. It becomes a protostar, surrounded by a rotating disk of gas and dust. The rotation comes from the cloud's original angular momentum. Even if the rotation at the start was very slow, contraction conserves this motion, forcing the spin to increase as the material shrinks. This explains why nearly every forming star is surrounded by a disk, and why most planets eventually form in the same plane as their parent star's equator. The early protostar does not yet shine by nuclear fusion. Its light comes from gravitational contraction, the slow conversion of potential energy into heat and radiation. This phase can last a few million years, depending on the mass of the forming star. The smaller the object, the slower this process. Astronomers call this period the Kelvin-Helmholtz contraction phase. It marks the stage when the object gradually changes from a collapsing cloud to a stable, shining star. During this time, jets of material often appear at the poles of the protostar. These narrow streams of gas, called bipolar outflows, help remove angular momentum from the system. By pushing material outward, they allow the rest of the gas to fall inward more efficiently. Observations in radio and infrared wavelengths show these jets stretching for light years, carving cavities into the surrounding cloud. They are visible evidence that gravity's slow work is almost done. As the protostar grows, its interior becomes layered. The temperature in the center keeps increasing, while the outer regions remain cooler. Radiation from the core travels outward, gradually clearing away the surrounding dust. Eventually, the cloud thins enough for visible light to escape. The star becomes optically visible for the first time, a young T Tauri star, named after the prototype object discovered in the Taurus constellation. At this point, the internal pressure from the heated gas is almost strong enough to balance gravity. The protostar vibrates slightly, adjusting toward equilibrium. These vibrations cause changes in brightness that can be detected with precision instruments. Each oscillation carries information about the star's internal density and structure, forming a field of study known as asteroseismology. The process is slow but precise. Gravity does not simply pull everything into a single point. It balances collapse and pressure to form a stable structure. This balance, called hydrostatic equilibrium, is the same principle that will later define the star's long-term stability during its main sequence life. When the temperature in the core finally exceeds 15 million degrees, hydrogen nuclei begin to fuse into helium. That moment marks the end of gravity's dominant phase and the beginning of nuclear fusion as the new source of energy. The star stops shrinking, its internal pressure steadies, and its light becomes constant. The quiet work of gravity is complete, replaced by the steady burn of fusion that will continue for billions of years. Understanding this stage is essential for all of astrophysics. The same equations that describe this collapse also explain the formation of planets, moons, and galaxies. Gravity sets the framework for structure everywhere in the universe. It is the reason gas becomes a star, the reason stars group into clusters, and the reason galaxies hold their shape. Everything begins with the same rule: matter attracts matter, and over time, attraction creates order. As you rest, imagine this slow gathering process continuing silently in the dark of space. Each atom, pulled by the faintest force, joins the next. Over millions of years, gravity sculpts chaos into form, just as your body, in rest, quietly returns to balance. When gravity has gathered enough material into the forming protostar, the internal temperature begins to climb rapidly. Deep inside, the density is now high enough that each atom collides with many others in a fraction of a second. The gas no longer behaves as a simple collection of particles. It becomes a plasma, a state of matter where electrons are separated from atomic nuclei and move freely. This transformation changes how energy moves through the interior and prepares the conditions for fusion. At this stage, the energy source is still gravitational contraction. Every time the protostar shrinks a little more, potential energy is converted into heat. The surface glows in infrared wavelengths, which can be detected by specialized telescopes. Although this radiation is invisible to the human eye, it represents the first sign that the star is producing measurable energy. Astronomers describe the balance of forces at this point using the virial theorem, which relates the total kinetic energy of the gas to its gravitational potential energy. It explains why the star heats as it contracts rather than cooling. The temperature at the center continues to rise. When it reaches around 1 million degrees, new reactions start to occur between the particles, though they are not yet nuclear reactions. Instead, the plasma becomes ionized enough for energy to transfer efficiently by radiation and convection. Convection occurs when hot material rises and cooler material sinks, setting up large-scale motion inside the protostar. These currents help distribute heat evenly and mix the interior material. The growing energy from compression begins to affect the outer layers. They start to expand slightly, slowing the rate of collapse. The protostar moves toward a temporary balance, known as quasi-hydrostatic equilibrium, where the inward and outward pressures almost cancel. However, this balance is not stable. Gravity continues to work, though more slowly, maintaining the gradual rise in temperature. Around this time, the rotation of the surrounding disk influences the developing system. Dust and ice particles collide within the disk, sticking together due to electrostatic forces. Over time, these clumps grow into centimeter-sized pebbles and later into kilometer-sized planetesimals. The foundations of planets form while the star is still incomplete. This shows that stellar and planetary formation are not separate events, but parts of one continuous process. Inside the protostar, radiation struggles to escape. The gas is still opaque, so photons bounce millions of times before reaching the surface. This makes the cooling process extremely slow. The protostar's brightness changes very little from day to day, though its internal structure evolves continuously. Observations and computer models indicate that such an object can remain in this stage for a few million years, depending on its mass. As temperature climbs toward 10 million degrees, the protons in the core begin to move at speeds close to 1/10 the speed of light. Collisions between them become frequent and energetic enough to overcome their electrical repulsion. Fusion is now near the threshold. When the first hydrogen nuclei combine to form helium, energy is released in the form of gamma rays and neutrinos. At that moment, the protostar becomes a main sequence star. The ignition of fusion is not explosive. It happens gradually, stabilizing the core and stopping the collapse. From this point onward, the outward pressure created by radiation exactly balances the inward pull of gravity. The young star enters a long period of stability, shining steadily for billions of years. The first warmth that once came from contraction now comes from nuclear reactions. The light that escapes into space is the same energy that maintains this balance. A new star has been born, and for the first time, it stands in equilibrium, a state that marks the true beginning of its life. When you observe a calm night sky, remember that each shining point has passed through this same transformation. Every star you see was once a faint, heating sphere, hidden in darkness, waiting for its first sustained reaction. Just as your body settles into steady breathing before sleep, the star finds its rhythm, pressure, and gravity in perfect balance, light flowing quietly outward. At the center of the newly formed star, the temperature now exceeds 15 million degrees. Under these extreme conditions, the motion of hydrogen nuclei becomes fast enough to overcome their natural repulsion. When they collide, they fuse into helium, releasing large amounts of energy. This process is known as nuclear fusion, and it marks the transition from a collapsing protostar to a stable, self-sustaining star. The fusion process in most stars like our Sun follows what is called the proton-proton chain reaction. In this sequence, two protons first combine to form a heavier particle called deuterium, releasing a positron and a neutrino. Then, the deuterium nucleus fuses with another proton to create helium-3. Finally, two helium-3 nuclei merge to form helium-4, releasing two protons that return to the chain. Each complete cycle converts a small fraction of mass into energy according to Einstein's equation E equals mc, 2E equals mc2, E equals mc2. The result is a steady release of energy that powers the star's light. Inside the core, this energy moves outward through two main mechanisms: radiation and convection. In the radiative zone, photons are absorbed and re-emitted countless times by atoms, gradually losing energy as they travel outward. The journey of a photon from the center of a star to its surface can take hundreds of thousands of years. In the outer convective layers, rising and falling currents of hot gas transport energy more directly. The combination of these processes establishes a stable flow of heat from the core to space. As fusion continues, the star's internal structure adjusts to maintain hydrostatic equilibrium, the balance between the inward pull of gravity and the outward pressure of radiation and gas. If fusion slows, gravity compresses the core slightly, raising temperature and pressure until the reaction rate increases again. If fusion speeds up, expansion cools the core and slows the reactions. This automatic regulation allows the star to remain stable for most of its life. The surface temperature of the new star determines its color and brightness. Hotter stars emit more blue light, while cooler ones appear red. The relationship between a star's luminosity, temperature, and size is described by the Hertzsprung-Russell diagram, a key tool in astrophysics that shows how stars evolve over time. The position of a star on this diagram depends primarily on its mass. High-mass stars burn their fuel quickly and live short, brilliant lives. Low-mass stars burn more slowly and can last for tens of billions of years. The Sun, a medium-mass star, will spend about 10 billion years on the main sequence, the long, stable phase of stellar evolution. During this time, it converts roughly 4 million tons of mass into energy every second, though this represents only a tiny fraction of its total mass. The ignition of fusion transforms the surrounding environment as well. The radiation from the newborn star pushes away remaining gas and dust, clearing the region where it was born. What was once a dense, opaque cloud becomes a bright, open space filled with light. The star's intense ultraviolet radiation can ionize nearby hydrogen, forming an H-tie region that glows pink or red in astronomical images. These nebulae mark places in galaxies where new stars are being born. For astronomers, observing this transition provides direct insight into how energy generation shapes the universe. Fusion is not only the power source of stars, it is the origin of nearly all visible light in the cosmos. Every photon of sunlight, every sparkle in the night sky is a direct result of this reaction. As the star settles into its new balance, fusion will continue quietly and efficiently for most of its existence. The process that began with collapsing gas now enters a long period of steady order. The first burst of ignition gives way to calm stability. The star no longer changes quickly, it simply shines. If you look up at a star tonight, the light you see began with this same ignition. It is energy born in a core of fusion, traveling across space until it reaches your eyes. In that moment, you are seeing not just brightness, but the physics of balance, the same principle that keeps both stars and living systems stable over time. Once nuclear fusion has begun, the star enters the main sequence phase, the longest and most stable part of its life. During this period, hydrogen atoms in the core fuse continuously into helium, releasing energy that maintains balance between the inward pull of gravity and the outward push of radiation. This balance, called hydrostatic equilibrium, ensures that the star keeps a nearly constant size, temperature, and brightness for millions or even billions of years. The structure of the star during this stage depends primarily on its mass. More massive stars have hotter cores, where fusion proceeds at a much higher rate. They shine intensely but exhaust their fuel quickly, living only a few million years. Smaller stars, with cooler cores, burn their hydrogen slowly and can remain stable for tens of billions of years. Our Sun sits roughly in the middle of this scale, steady, moderate, and long-lived. Inside the core, fusion reactions maintain a constant energy output. The released energy moves outward by radiation and convection, depending on the star's internal composition. In the radiative zones, photons are absorbed and re-emitted thousands of times before reaching the outer layers. In the convective zones, large bubbles of hot gas rise, release their energy, and sink again. These cycles transport heat efficiently and give the star's surface a dynamic texture that astronomers can measure through small changes in brightness. At the surface, the energy radiates into space as visible light, ultraviolet, and infrared. The star's spectral type, ranging from blue O-type to red M-type, depends on surface temperature. Blue stars exceed 25,000 degrees Celsius, while red stars are cooler, often below 3,000 degrees. The Sun, at about 5,500 degrees, is classified as a G-type star. This classification helps scientists understand a star's temperature, age, and energy output with remarkable precision. The light emitted by a star also affects its surroundings. Radiation pressure pushes away leftover gas and dust, clearing the space where planets may form. The remaining material in the surrounding disk can cool and clump together, forming rocks, asteroids, and eventually planets. This is why many main sequence stars are accompanied by planetary systems. The process of stellar formation naturally leads to planetary creation. For most of its lifetime, a star changes very little. It produces energy at a stable rate, maintaining the same temperature and luminosity for billions of years. However, subtle processes continue within. The helium ash produced by fusion accumulates in the core, gradually increasing the density. As the hydrogen fuel is consumed, the core composition shifts, setting the stage for future changes. These internal adjustments happen slowly and are invisible from the outside, but they determine how the star will evolve when its hydrogen supply runs low. During the main sequence phase, stars are remarkably efficient. Only a small fraction of the hydrogen in the core needs to fuse to produce immense and continuous energy. The radiation from a single star can support entire planetary ecosystems, drive weather patterns, and influence the chemistry of surrounding space. This steady power supply makes stars the most reliable engines in the universe. The main sequence can be thought of as stellar adulthood, long, stable, and productive. The physical laws governing this stability are universal. Gravity and pressure remain balanced, fusion remains constant, and temperature fluctuations are minimal. For a star like the Sun, this period will last roughly 10 billion years. Only when most of the hydrogen in the core is exhausted will the balance begin to shift. For now, the star's life is calm. Its light travels freely through space, illuminating other worlds and, eventually, the surface of Earth. When you see starlight in the night sky, you are seeing the steady outcome of this balance: matter transformed into energy, energy transformed into light, and light traveling across unimaginable distances to meet your eyes. In the youth of a star, the universe finds long-lasting order, proof that even the most powerful systems can remain peaceful when equilibrium is maintained. The energy produced in the core of a star travels outward in the form of light. Each photon begins its journey as a packet of energy released during fusion. It moves through layers of dense plasma, scattering millions of times before escaping into space. Once free, the photon travels at the speed of light, continuing indefinitely unless absorbed by matter along the way. When this light reaches planets, it becomes the foundation of everything that can live. On Earth, it warms the oceans, drives weather systems, and fuels photosynthesis in plants. The same light that left the Sun 8 minutes ago now supports entire ecosystems. Stars are therefore not just points of brightness, they are energy sources that connect distant regions of the cosmos. The color of starlight tells us much about its origin. Blue light carries higher energy and comes from hotter stars, while red light comes from cooler ones. Instruments such as spectrographs split light into a spectrum, allowing scientists to analyze its composition. The dark lines in a star's spectrum reveal which elements are present in its atmosphere. This method, called spectroscopy, is one of the most powerful tools in astronomy. It allows us to determine a star's temperature, velocity, and even chemical makeup from light years away. Light also interacts with the space it passes through. Dust and gas absorb certain wavelengths and scatter others, changing a star's apparent color. This effect, known as interstellar reddening, is similar to the way Earth's atmosphere makes the Sun appear red at sunset. Observations must be corrected for this effect to measure a star's true properties. The careful study of how light behaves in space has helped astronomers map distances, discover exoplanets, and trace the evolution of galaxies. Beyond its scientific role, light has a physical influence on matter. Radiation pressure, the momentum carried by photons, can push on dust grains, drive stellar winds, and shape entire nebulae. Over time, this pressure clears away the gas left from star formation, leaving behind open clusters of newly born stars. These processes demonstrate how light acts not only as a messenger, but also as an agent of change. For humans, light defines the rhythm of life. The body's internal clock, or circadian rhythm, is synchronized to the daily cycle of sunlight and darkness. When the sun sets, the decreasing light signals the brain to produce melatonin, a hormone that promotes sleep. This natural rhythm evolved under the constant influence of stellar radiation. Every night, As the planet turns away from the sun, the absence of light triggers biological systems to rest and restore balance. Even faint starlight contributes to this cycle. Long before artificial lighting, people navigated their sleep and wake patterns by the stars. The dim glow of the Milky Way served as the final light before darkness. It guided early explorers, farmers, and travelers, linking human behavior to cosmic motion. Today, the same photons that left distant stars thousands of years ago still reach us, gently reminding the body of the difference between day and night. When you prepare to sleep, your body follows the same principle that governs the universe: alternation between energy and rest. The star radiates energy outward. The human body, receiving that energy, eventually turns it inward, slowing metabolism, lowering temperature, and restoring equilibrium. Light and sleep are two sides of the same natural balance. Lying under a dark sky, the faint light you see has traveled across unimaginable distances to reach you. Each point of brightness represents a process that began billions of years ago: gravity, fusion, and the steady emission of photons. That light passes through space, through atmosphere, and finally rests upon your eyes. In that moment, you are part of the same system: energy moving outward, awareness moving inward. A star's stability depends on one of the simplest and most important relationships in physics: the balance between gravity and pressure. Gravity pulls all mass inward, while pressure from hot gas and radiation pushes outward. When these two forces are equal, the star remains stable. This condition is called hydrostatic equilibrium, and it defines the main sequence phase of stellar life. The source of the outward pressure is the energy released from nuclear fusion in the core. Every second, enormous amounts of energy flow outward, pushing against the weight of the outer layers. At the same time, gravity continues to pull everything toward the center. If the energy production in the core changes, the star immediately responds. A slight increase in fusion raises the pressure, causing the outer layers to expand and cool, which slows the reaction. If fusion slows down, the star contracts, heating the core and restoring balance. This automatic regulation keeps the star's size and brightness nearly constant over long timescales. The mathematics behind this equilibrium can be expressed by the equation of hydrostatic balance, which relates the pressure gradient inside a star to its density and the local gravitational field. In simple terms, the deeper you go inside a star, the higher the pressure must be to support the weight above. At the core, pressures reach hundreds of billions of times that of Earth's atmosphere, enough to confine the plasma and sustain fusion. The same physical principles that govern stellar balance also appear in other systems. In planetary atmospheres, for example, the pressure decreases gradually with altitude according to the same basic law. Understanding hydrostatic equilibrium allows scientists to model not only stars, but also gas giants like Jupiter and Saturn. The concept links phenomena across vastly different scales, from laboratory plasmas to galaxies. Inside a star, equilibrium is not static, it is a continuous process. Energy moves outward by radiation and convection, while gravity constantly acts inward. The two processes never stop, they remain in dynamic balance. This makes stars remarkably resilient. Even disturbances such as magnetic activity or rotation cause only small fluctuations. The Sun, for instance, varies in brightness by less than 0.1% over its 11-year magnetic cycle. The outer layers of a star respond differently depending on its temperature and composition. In hotter stars, radiation pressure dominates, while in cooler stars like the Sun, gas pressure and convection are more significant. Despite these differences, the result is the same: a stable star capable of shining steadily for billions of years. This balance also determines how a star will age. Over time, as hydrogen is converted to helium, the mean molecular weight in the core increases, the gas becomes denser, and the star gradually adjusts to maintain equilibrium. These subtle changes lead to slow increases in brightness and size over billions of years. The process is so gradual that for most of its lifetime, a star's behavior seems unchanged. The concept of balance in stellar physics mirrors balance in biological systems. Human bodies maintain equilibrium through processes like temperature regulation, blood pressure control, and energy metabolism. In both cases, the system adjusts automatically to remain stable. The principle is universal. Nature resists extremes by seeking balance between opposing forces. For astronomers, studying this equilibrium provides a way to understand stellar interiors that cannot be observed directly. Through the analysis of vibrations on a star's surface, a method known as asteroseismology, scientists can infer internal densities, pressures, and rotation speeds. The same physics that maintains balance also produces measurable oscillations that carry information outward. The calm light of a star is the visible sign of this hidden harmony. Gravity and radiation, two powerful and opposite forces, meet perfectly in the middle. The result is not conflict but stability. Proof that even in the most extreme environments, balance creates order. When you look at a steady star, you are seeing equilibrium made visible, a silent demonstration of how nature sustains itself through continuous, precise adjustment. Every star emits light across a wide range of wavelengths, from high-energy ultraviolet to low-energy infrared. When this light is dispersed through a prism or a spectrograph, it forms a continuous band of colors known as a spectrum. Yet the spectrum is not perfectly smooth. It contains dark lines, specific wavelengths where light is missing. These lines, called absorption lines, reveal the elements present in the star's atmosphere. Each element absorbs light at unique wavelengths, creating a distinct pattern that acts like a fingerprint. Hydrogen leaves a characteristic set of lines known as the Balmer series, visible in the blue and red regions of the spectrum. Sodium, calcium, and iron each have their own identifiable marks. By comparing observed spectra with laboratory measurements, astronomers can determine which elements exist in a star and in what proportions. Spectroscopy is one of the most powerful tools in astronomy because it allows scientists to study objects that are far beyond physical reach. From the spectrum of a star, they can infer temperature, chemical composition, pressure, and even surface gravity. The spacing and intensity of the absorption lines provide clues about the density and motion of the gases in the star's atmosphere. The shape of the overall spectrum reveals a star's surface temperature. According to Planck's law, a perfect thermal emitter, called a blackbody, produces a spectrum whose peak shifts toward shorter wavelengths as temperature increases. Hotter stars therefore appear blue, while cooler stars emit more red light. This relationship is summarized in Wien's law, which links color to temperature in a simple mathematical form. The study of spectra thus provides direct access to physical conditions that cannot otherwise be measured. Beyond chemical and thermal information, spectra also show how stars move. When a star approaches or recedes from the observer, its light waves are slightly compressed or stretched, a phenomenon known as the Doppler effect. This causes the spectral lines to shift toward shorter wavelengths, blue shift, or longer wavelengths, red shift. Measuring these shifts allows astronomers to calculate the star's radial velocity. The same principle is used to detect exoplanets, as their gravitational pull causes subtle, periodic wobbles in the star's spectrum. In binary star systems, two sets of spectral lines often appear, moving back and forth as the stars orbit each other. Careful analysis of these movements provides precise measurements of stellar masses. Because mass determines nearly every aspect of a star's evolution, spectroscopy has become essential for understanding how stars live and die. Spectral analysis also extends beyond individual stars. When the light from a galaxy is examined, it contains the combined spectra of billions of stars, plus the signatures of interstellar gas. These composite spectra help scientists estimate the age, composition, and rate of star formation in distant galaxies. The same principles that describe a single star's light scale up to describe the largest structures in the universe. Even the sun's spectrum, studied in detail since the 19th century, continues to provide insights. The dark lines known as Fraunhofer lines were first observed through simple prisms, and today they serve as the foundation of modern solar physics. High-resolution instruments aboard space telescopes measure how these lines change during solar activity, revealing information about temperature, motion, and magnetic fields. When you look at a star, its light appears simple and white, but hidden within that light is a complete record of the star's physical state. Each photon carries information about the conditions it passed through before escaping the surface. In a sense, the spectrum is the star's autobiography, written in lines of color and energy, legible to anyone who knows how to read it. Although many people picture stars as isolated objects, more than half of the stars in our galaxy exist in binary systems, pairs of stars bound by mutual gravity. In some cases, these systems include 3 or more members, forming small clusters called multiple star systems. Studying how stars interact in these environments provides important insight into stellar evolution, mass transfer, and the dynamics of orbits. Binary systems form naturally from the collapse of a rotating molecular cloud. As the cloud contracts, small irregularities in density can cause it to split into 2 or more dense cores. Each core gathers material, eventually becoming a separate star. The gravitational connection between them ensures that they remain bound in orbit around a shared center of mass, known as the barycenter. The characteristics of a binary system depend mainly on the distance between the stars. Wide binaries can be separated by hundreds or thousands of astronomical units, moving slowly in large orbits. They influence each other only through gravity. Close binaries, however, may be only a few stellar radii apart. In these systems, tidal forces and mass exchange can dramatically alter each star's development. One common type of close binary is the eclipsing binary, where the stars periodically pass in front of each other as seen from Earth. This alignment causes regular changes in brightness, which can be measured with high precision. By studying the timing and depth of these eclipses, astronomers can determine the orbital period, size, and even the masses of both stars. These measurements provide some of the most accurate data available for testing models of stellar structure. Another important class is the spectroscopic binary, identified through shifts in spectral lines caused by the Doppler effect. As the stars orbit their barycenter, their light alternately shifts toward blue and red wavelengths. Even when the stars cannot be seen separately, their motion leaves a measurable trace in their spectra. Combining this data with orbital models allows astronomers to calculate orbital velocities and estimate masses. In very close systems, gravitational interaction can lead to mass transfer. If one star expands during its red giant phase and fills its Roche lobe, the region where its gravity dominates, material can flow toward the companion star. This transfer can form an accretion disk around the receiving star, heating it and producing strong X-ray or ultraviolet emissions. Over time, such interactions can reverse the star's evolutionary order, with the less massive star becoming more evolved. Some binary systems evolve into cataclysmic variables, where mass transfer becomes unstable and triggers outbursts or nova events. Others may end with one component collapsing into a white dwarf, neutron star, or black hole, continuing to draw material from its partner. These interactions are laboratories for studying extreme physics, including high-energy radiation and relativistic motion. Not all effects of binary companionship are violent. In many pairs, the stars evolve independently, their orbits remaining stable for billions of years. Observations of wide binaries help astronomers test theories of stellar motion within the galaxy and refine distance measurements through parallax. Because both stars form from the same cloud, they share nearly identical compositions, allowing comparisons that isolate the effects of mass and temperature. Binary systems also influence planetary formation. In close pairs, gravitational perturbations can prevent stable planetary orbits, but in wider binaries, planets can orbit both stars or just one. The study of such systems expands understanding of how common habitable worlds may be across the galaxy. Binary stars demonstrate that gravity can create lasting relationships as well as isolated stability. Their interactions show how mass, distance, and time shape evolution in countless variations. When you observe a single point of light in the night sky, you may be looking at two or more stars orbiting each other so closely that their combined light appears as one, a quiet partnership maintained by gravity's unbroken pull. Stars are rarely born alone. Most originate in clusters, groups of stars that form from the same molecular cloud at roughly the same time. The shared origin means that the stars within a cluster have similar chemical compositions but often differ in mass. These differences allow astronomers to study stellar evolution by comparing how stars of various masses change under nearly identical conditions. Two main types of star clusters exist: open clusters and globular clusters. Open clusters, such as the Pleiades or Hyades, contain a few dozen to several thousand stars loosely bound by gravity. They are relatively young, often only a few 100 million years old, and are found mostly in the spiral arms of galaxies. The stars in open clusters eventually drift apart as they interact with interstellar gas and with the gravitational pull of the galactic disk. Globular clusters, on the other hand, are much older and more tightly bound. They contain hundreds of thousands of stars packed into spherical shapes that can span more than 100 light-years across. These clusters orbit the galactic center in the outer halo, far from the disk where new stars are born. Their ages, typically around 10 to 12 billion years, make them some of the oldest observable structures in the universe. The stars within globular clusters are mostly low mass and metal poor, preserving the chemical makeup of the early universe. The formation of clusters begins inside large molecular clouds. When parts of a cloud collapse under gravity, multiple dense cores can form close together, each becoming a protostar. Because they share the same environment, the new stars interact gravitationally, forming groups that stay together for millions of years. In young clusters, residual gas and dust often remain, illuminated by the ultraviolet radiation of massive newborn stars. This creates emission nebulae, bright regions of glowing hydrogen that trace the outlines of the cloud. Over time, stellar winds and radiation from the cluster's most massive stars blow away the remaining gas. Without this extra material, the gravitational binding weakens. Open clusters begin to disperse, releasing their members into the galaxy. The Sun itself likely formed in such a group more than 4 billion years ago, though its siblings have since drifted far apart. Astronomers search for these long-lost relatives by matching chemical signatures in nearby stars, a field known as chemical tagging. Cluster studies are essential for understanding stellar lifetimes, because all the stars in a cluster share an age. Plotting their brightness and color on a Hertzsprung-Russell diagram shows a clear pattern. The point where stars begin to leave the main sequence, the turn-off point, reveals the cluster's age. This method has become one of the most reliable ways to date stellar populations and, by extension, to estimate the age of the Milky Way itself. Clusters also serve as reference points for measuring distances across space. By comparing their observed brightness to theoretical models, astronomers can calibrate the distance ladder, a sequence of techniques that link local measurements to distant galaxies. Their importance in astronomy extends far beyond their beauty. They are tools for precision and calibration in almost every branch of astrophysics. Despite their scientific value, star clusters are temporary structures. Open clusters dissolve over hundreds of millions of years, while globular clusters will eventually lose stars through tidal interactions with their host galaxies. Yet during their lifetimes, they shape galactic structure and seed new regions of star formation through gravitational encounters. When you look at the night sky, the bright patches that seem like single stars may in fact be clusters, families of suns sharing a common birth and history. Each one is a reminder that stars, like people, often begin their journeys together before drifting apart to follow their individual paths through space. Inside every active star, nuclear fusion continues to transform simple elements into more complex ones. In its core, hydrogen is steadily converted into helium, but the process does not end there. As a star ages and its hydrogen supply decreases, temperature and pressure in the core rise high enough to allow new reactions. These reactions create the heavier elements that astronomers refer to collectively as metals, a term that, in astrophysics, includes everything heavier than helium. The path of element creation depends on the star's mass. In stars similar to the Sun, fusion stops after helium becomes carbon and oxygen. Temperatures never climb high enough to sustain further reactions. In massive stars, however, the internal heat can exceed several 100 million degrees, igniting additional stages of fusion. Each stage burns a different element. Helium becomes carbon, carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. This sequence, known as stellar nucleosynthesis, builds the periodic table directly from the energy released in the core. The reactions that create these elements follow strict physical rules. Every step must release more energy than it consumes. For light nuclei, such as hydrogen and helium, fusion produces energy. But when the process reaches iron, further fusion no longer yields a net gain. Iron marks a boundary. Beyond it, additional fusion absorbs energy rather than releasing it. This limit determines how far a star can evolve before it becomes unstable. While fusion takes place in the core, other processes occur in the surrounding shells. Convection mixes material, carrying newly formed elements toward the outer layers. Stellar winds then eject part of this material into space, spreading carbon, nitrogen, and oxygen into the interstellar medium. Even before a star's death, it is already enriching its surroundings with building blocks for future worlds. Spectroscopic studies confirm this recycling. By examining the spectral lines of old and young stars, astronomers can trace how the concentration of heavy elements, called metallicity, changes over time. Young stars in the Milky Way's disk contain higher metallicity because they formed from gas already enriched by earlier generations of stars. This gradual chemical evolution explains how planets with complex minerals and, eventually, life could exist. Not all element production occurs quietly. Some requires violent conditions. During the final collapse of a massive star, a supernova explosion provides the extreme energy needed to create the heaviest elements, gold, uranium, and others, through rapid neutron capture. These elements, though rare, spread widely across galaxies, embedded in dust that later condenses into new systems. The gold in a ring, the calcium in bones, and the iron in blood all originated in such events. Computational models and stellar observations agree on the overall efficiency of this cosmic factory. Only about 2% of a galaxy's mass is locked in heavy elements. Yet those elements define nearly every structure visible to us: planets, atmospheres, and living organisms. The rest remains as hydrogen and helium, continuing to fuel new generations of stars. When you look at the night sky, Every point of light represents an active laboratory of chemistry and physics. Inside each star, matter is being transformed from the simplest form to the ingredients of complexity. The term metal maker describes not just an astronomical object but a universal process, energy turning simplicity into diversity. It is through these steady reactions that the universe builds itself, one fusion event at a time. The light that leaves a star travels through space for years, centuries, or sometimes millennia before it reaches another world. Each photon that arrives at Earth carries the history of the reaction that created it, the temperature, composition, and density of the star from which it came. As this light passes through the atmosphere, it scatters, softening its brilliance and spreading across the landscape. What remains is a gentle, diffused glow that has influenced life on this planet for as long as it has existed. Human biology evolved under this continuous cycle of light and darkness. Sunlight signals activity and growth. Its absence signals rest and restoration. The setting of the sun lowers light intensity by 1,000,000 times, allowing the brain's suprachiasmatic nucleus, the body's internal clock, to switch from wakefulness to preparation for sleep. The hormone melatonin begins to rise, lowering heart rate and body temperature. In this quiet transition, starlight becomes the faintest trace of the day that has passed, a reminder that the world remains illuminated even in rest. The starlight visible at night is ancient. Many of the photons entering your eyes began their journey before human civilization existed. Some left their source when mammals were still new to Earth. The atmosphere bends and filters them, allowing only a small portion to reach the surface. Most are too weak to affect sight strongly, but their collective presence creates the background glow we recognize as the night sky. To the human eye, this light is near the threshold of perception. To the body, it is part of the rhythm that defines day and night. Astronomers measure this faint light precisely. Instruments called photometers and spectrographs can detect individual photons, record their wavelength, and determine the star's distance and type. The data reveal that starlight reaching Earth varies slightly over time as the planet orbits the Sun, producing subtle changes in brightness known as the seasonal variation of the night sky. These cycles are consistent enough that early civilizations used them to track seasons and time long before written calendars existed. From a physical perspective, the light you see when you look upward has been traveling straight since it left its source. Space does not slow it or drain its energy significantly. Each photon continues at the same speed, about 300,000 kilometers per second, until it interacts with matter. When one of those photons touches the retina, it is absorbed by a molecule of rhodopsin in a rod cell, triggering an electrical signal that the brain interprets as light. In this way, something that began as nuclear fusion billions of kilometers away becomes perception, memory, and thought. This connection between stellar light and human biology is both simple and profound. The same energy that powers photosynthesis during the day influences rest at night. Even in darkness, your body aligns with a rhythm that began in the stars. When you close your eyes, the remaining light on your skin fades slowly, and the nervous system moves towards stillness. Sleep follows naturally because the signals that guide it are written into the design of light itself. As you drift towards sleep, consider that the light fading around you has traveled unimaginable distances to arrive here. Some of it comes from nearby suns within our galaxy. Some comes from stars thousands of light years away. None of it was directed at you, yet all of it passes through you, absorbed by your eyes, your skin, and even the molecules of the air you breathe. The starlight that fills the night sky is the universe's quiet signature, evidence that energy and rest are two parts of the same ongoing process. A star's youth is defined by balance, but that balance does not last forever. Over time, the hydrogen in the core, the fuel for nuclear fusion, slowly diminishes. As hydrogen atoms fuse into helium, the number of particles able to sustain the reaction decreases, and the fusion rate begins to change. The core gradually contracts under its own gravity, raising its temperature and pressure. This marks the beginning of a star's aging process, the slow transition away from the stable main sequence. In stars similar to the Sun, the buildup of helium in the center plays a key role. Helium does not fuse under the same conditions as hydrogen, so the core no longer produces enough energy to counteract gravity. As the core contracts, the surrounding shell of hydrogen becomes hotter and begins fusing more rapidly. The increased energy output pushes the outer layers outward, causing the star to expand. Its surface cools as it grows, and its color shifts from yellow or white to orange and red. The star becomes what astronomers call a subgiant, then a red giant. The changes in temperature and size are governed by the same physical laws that maintained stability earlier in life, but the balance point has shifted. The outer envelope of the star expands by a factor of tens to hundreds, while the core shrinks to a fraction of its original volume. The star's total brightness actually increases because its enlarged surface area emits more light, even though each square meter of that surface is cooler. This process happens very gradually. For a star like the Sun, the main sequence phase lasts around 10 billion years, while the expansion into a red giant takes a few 100 million. Observations of older stars in open clusters show this pattern clearly. Younger, hotter stars remain on the main sequence, while older, cooler, and larger stars move upward and to the right on the Hertzsprung-Russell diagram, a graphical record of stellar evolution. In more massive stars, the transition is faster and more dramatic. Their larger cores produce higher temperatures, allowing helium fusion to begin sooner. The outer layers expand and contract multiple times, creating a series of pulses that cause the star to brighten and dim periodically. These stars, known as Cepheid variables, are critical for measuring cosmic distances because their brightness variations follow precise relationships with their intrinsic luminosity. During this aging process, stars also begin to lose mass. Strong stellar winds carry gas and dust into space, forming expanding shells around the star. These outflows enrich the interstellar medium with carbon, nitrogen, and oxygen, materials that later become part of new clouds, planets, and life forms. In this way, even as stars grow unstable, they contribute to the continuity of cosmic chemistry. The transformation from a stable star to an aging one is not an abrupt failure but an adjustment. The same physics that once maintained equilibrium continues to operate, only now the conditions force a different outcome. Fusion continues, but in new regions and at new rates. Gravity still compresses, radiation still expands, and the balance still exists, just in a more complex form. From a human perspective, the aging of stars is far too slow to observe directly, yet the evidence surrounds us in the light of evolved stars scattered across the sky. Their spectra show cooler temperatures and richer elemental compositions, signs that they have entered later stages of life. Studying them allows astronomers to understand not only the Sun's eventual fate but also the broader cycles of transformation that define the universe. When a star ages, it does not simply fade, it evolves. The change from youth to maturity, from steady fusion to expansion, reflects the same principle seen throughout nature. Systems adapt to maintain balance under new conditions. The life of a star, even in decline, is a record of persistence, energy finding new forms to continue the story of matter and light. As a star leaves the main sequence, the changes in its core and atmosphere become increasingly pronounced. The inner region contracts under gravity, while the outer layers expand dramatically. What was once a compact, stable sphere grows to hundreds of times its original diameter. The star becomes a red giant, one of the most recognizable and studied stages in stellar evolution. The red giant's core is small, dense, and composed mainly of helium produced during the main sequence phase. Surrounding it is a shell where hydrogen continues to fuse into helium at a rapid rate. The energy from this shell-burning layer pushes outward, inflating the star's envelope. Because this expanding surface area is enormous, the temperature drops to around 3,000 degrees Celsius, cooler than before, giving the star its distinct reddish-orange hue. Inside the core, pressure and temperature continue to climb. When the temperature reaches about 100 million degrees, helium nuclei begin to fuse into carbon and oxygen in a process called the triple alpha reaction. 3 helium atoms combine to form a single carbon atom, releasing energy. In slightly more massive stars, some of this carbon fuses further into oxygen. This stage marks the beginning of a new form of fusion that sustains the star temporarily. The ignition of helium fusion is not gradual. In stars with masses similar to the Sun, the process begins suddenly in what is known as the helium flash. The core, composed of degenerate matter, resists expansion until fusion becomes so intense that it releases energy explosively, though the outer layers barely respond. For more massive stars, this transition occurs smoothly because their cores are less degenerate. After helium fusion stabilizes, the star settles into a new balance for several 100 million years, shining steadily as a horizontal branch star. The physical structure of a red giant is extreme. The core may contain half of the star's total mass compressed into a volume comparable to Earth, while the outer layers stretch far beyond the orbit of Mercury. The density difference between core and surface can span 12 orders of magnitude. Convection dominates the outer envelope, mixing material from deep inside with the surface. This process brings heavier elements, such as carbon and nitrogen, to the atmosphere, a phenomenon called dredge-up. Spectroscopic observations reveal these chemical changes. The atmospheres of red giants show absorption lines from molecules like titanium oxide and cyanogen, which do not exist in hotter stars. These molecules help astronomers identify red giants in distant galaxies and trace how stellar populations evolve. The changing composition of a star's outer layers also contributes to the gradual enrichment of interstellar gas. In the late stages of this phase, the star becomes increasingly unstable. Pulsations cause its brightness to vary over periods ranging from months to years. Some red giants eject significant amounts of mass through stellar winds, creating extended envelopes of dust and gas. These outflows will later form glowing shells known as planetary nebulae, marking the transition to the final stage of a low or medium mass star's life. The sight of a red giant is striking even from Earth. Stars such as Betelgeuse in Orion or Aldebaran in Taurus represent this stage, large, cool, and nearing the end of their nuclear burning. Though they appear calm, they are undergoing profound internal changes that will soon reshape them entirely. From a broader perspective, the rise of red giants shows how matter responds to exhaustion. When hydrogen fuel runs low, nature finds another path to release energy. The balance that once defined the main sequence gives way to new forms of stability, each temporary but necessary. The red giant phase is not a failure of the star's structure, but its adaptation to changing conditions, a reminder that transformation is an essential part of endurance. As a star expands into its red giant phase, the environment around it changes dramatically. The increase in luminosity and size alters the gravitational and thermal conditions for any surrounding planets. Worlds that once orbited at comfortable distances now face rising heat, shifting tides, and atmospheric loss. The transformation of the parent star marks the beginning of a difficult farewell between the star and the planetary system it once supported. For planets close to the star, the outcome is almost certain. As the star's outer layers expand, its radius may reach or even exceed the orbits of the inner planets. Any planet within that range will be engulfed. Temperatures climb high enough to vaporize rock, and friction within the extended atmosphere drags the planet inward. The material of the planet merges with the star's envelope, adding trace amounts of heavy elements to the outer layers. Even planets that remain outside the engulfed region experience severe changes. The star's increased radiation heats their surfaces, stripping away atmospheres and driving chemical reactions never possible before. The solar wind, now thousands of times stronger than during the main sequence, erodes any remaining gases. In some cases, magnetic fields can offer limited protection, but most atmospheres eventually dissipate into space. The gravitational structure of the system also evolves. As the star loses mass through steady stellar winds, its gravitational pull weakens. The orbits of surviving planets expand in response, moving them farther from the star. This outward migration can destabilize the system, causing smaller bodies such as asteroids or comets to shift into new trajectories. Collisions and ejections become more common as the delicate balance that once held the system together begins to change. Astronomers have observed examples of these processes in other star systems. In some red giant systems, infrared observations reveal rings or disks of dust, debris from disrupted planets, or evaporating comets. In extreme cases, remnants of planetary cores, known as planetary survivors, have been detected orbiting very close to evolved stars. These dense, metallic bodies are what remains after the outer layers of the planets were stripped away. They are evidence that even planetary destruction can leave behind traces of earlier worlds. As the red giant sheds its outer material, that material forms an expanding cloud around the star. Dust grains condense within the outflowing gas, creating the seeds of new planetary systems. When the outer layers are eventually lost completely, they form a planetary nebula, a glowing shell of gas illuminated by the hot core that remains. The nebula may last only tens of thousands of years, but during that time it contributes carbon, oxygen, and other elements to interstellar space. The process that ends one system's history lays the foundation for another's beginning. The final core that remains after the red giant phase will become a white dwarf, a dense, Earth-sized remnant that no longer fuses elements. The surviving planets, if any remain, will continue to orbit this faint star for billions of years. Their skies will no longer feature a brilliant sun, but a pale, slowly cooling ember. These remnants, observed around nearby white dwarfs, often show evidence of dust disks, the remains of disrupted asteroids and comets. From a broader view, planetary loss is not an isolated tragedy but a normal part of cosmic evolution. Stars and their planets share finite lifetimes governed by the same physical laws. The materials once locked in solid form, rocks, metals, and gases, will eventually be dispersed, recycled, and reused. The carbon from a destroyed world may later form part of a new planet, an atmosphere, or even a living cell elsewhere. When a star bids farewell to its planets, the process is both destructive and creative. It marks the end of one chapter in the long cycle of matter and energy. Nothing truly disappears. It simply changes form, following the same continuity that connects all stages of stellar and planetary evolution. As a star approaches the end of its active life, the processes within it slow and simplify. The core contracts while the outer layers thin and drift away. Fusion reactions occur in narrow shells, burning the remaining hydrogen and helium in cycles that grow shorter and weaker. The system no longer sustains itself through balance but through gradual release. It is the slow winding down of stellar energy, a transition from activity to quiet persistence. When a star expels its final layers, it leaves behind a small, dense core. This core glows with residual heat, shining faintly without further fusion. The surrounding gas expands outward, illuminated by ultraviolet radiation from the hot remnant. Astronomers see these objects as planetary nebulae, though they have no connection to actual planets. Their shapes, rings, bubbles, and filaments are sculpted by the interactions between stellar winds and magnetic fields. Over time, the gas disperses into space, leaving only the central remnant behind. That remnant, called a white dwarf, is roughly the size of Earth but contains half the mass of the Sun. Its matter is compressed into a dense state, supported not by thermal pressure but by electron degeneracy pressure, a quantum mechanical effect that resists further compression. The temperature of a white dwarf can exceed 100,000 degrees Celsius at birth, but without fusion, it cools slowly over billions of years. Eventually, it will fade into darkness, becoming a theoretical black dwarf, though the universe is not yet old enough for any to exist. The transition from red giant to white dwarf represents the star's last act of transformation. What remains is stability of a different kind, no longer powered by fusion, yet perfectly balanced between gravity and quantum pressure. The energy that once maintained planets and lighted worlds is now stored quietly within a sphere of compressed matter. Even in stillness, the laws of physics continue to operate with precision. This long cooling phase can be compared to rest after exertion. The star does not die in a single event. It enters a state of equilibrium where change slows nearly to a halt. Energy radiates gently into space, a process that may continue for longer than all of human history combined. In this way, the universe repeats the same rhythm found everywhere in nature: activity followed by recovery, energy followed by calm. For humans observing the night sky, this slow fading of light mirrors our own cycles of wakefulness and rest. Just as the body releases tension when it prepares for sleep, the star releases its last reserves of energy, settling into stillness. The difference is only one of scale. Both follow the same physical principles of conservation and equilibrium. In each case, stability emerges not from motion but from its gradual reduction. When you lie beneath a clear sky, many of the faintest points of light you see are white dwarfs, the remnants of stars that have completed their active lives. Their glow is the lingering warmth of processes long finished. In the quiet between your breaths, that same pattern continues: release, rest, and the preservation of balance. The life of a star ends not with a single moment of extinction but with an extended pause that carries forward the idea of continuity. The atoms that once composed its light will mix with interstellar gas, begin new cycles of motion, and eventually contribute to new stars. Nothing is wasted, and nothing truly ends. Just as your own sleep restores energy for the day ahead, the cooling of a star restores the conditions from which future creation will rise again. As a star nears the end of its fuel supply, the processes that once maintained balance become increasingly complex. Each layer of the star reacts differently to changing conditions, forming concentric shells where different elements undergo fusion. The sequence of these reactions depends primarily on the star's mass. In stars similar to the Sun, nuclear fusion stops after helium has been converted into carbon and oxygen. The core never becomes hot enough to ignite heavier elements, and further fusion is impossible. These stars end their active lives as white dwarfs, slowly cooling over billions of years. But in more massive stars, where core temperatures can reach several 100 million degrees, fusion continues through additional stages. At these extreme temperatures, helium-burning shells give way to carbon fusion, where carbon nuclei combine to form heavier elements such as neon, magnesium, and sodium. As the core becomes hotter, the reactions proceed faster. In just a few thousand years, a brief moment compared with the main sequence, the star passes through successive burning stages: neon burning, oxygen burning, and finally silicon burning. Each stage produces a new layer of ash, like the rings of a tree, marking the history of the star's energy production. The fusion of silicon into iron is the final step in this sequence. It represents the physical limit of energy generation through fusion. When two iron nuclei combine, they do not release energy. Instead, the reaction consumes it. At that point, the star's internal power source effectively shuts down. Without an outward flow of energy to counter gravity, the delicate balance that has sustained the star for millions of years collapses. The physics behind this collapse is straightforward but dramatic. With no pressure to oppose the inward pull of gravity, the core begins to contract rapidly. Densities climb to astonishing levels, trillions of kilograms per cubic centimeter, and the temperature spikes to billions of degrees. The contraction triggers the disintegration of atomic nuclei, breaking iron into smaller particles and flooding the core with free protons and neutrons. In a matter of seconds, the core's density becomes so high that electrons are forced into protons, forming neutrons and releasing neutrinos in vast numbers. This process, called neutronization, marks the creation of a new state of matter, an almost pure neutron core. The collapse continues until it reaches a critical point, where the density is high enough for neutron degeneracy pressure, a quantum mechanical resistance, to halt further compression. When the core stops collapsing, the outer layers, still falling inward at tremendous speed, strike the dense surface and rebound outward. This sudden reversal launches a shock wave through the star, leading to one of the most powerful events in the universe, a supernova explosion. The energy released in this final moment exceeds the total energy output of the star's entire main sequence life. The explosion disperses most of the star's mass into space, enriching the surrounding interstellar medium with newly formed heavy elements. Only the dense core remains, which will become either a neutron star or, if massive enough, a black hole. The final fusion stage demonstrates the ultimate limit of stellar endurance. Fusion, once the star's sustaining process, becomes the trigger for its end. The reactions that built complexity eventually reach a boundary where no further energy can be drawn. The collapse that follows is not failure, it is the inevitable transformation of energy into new forms. From the perspective of physics, this moment completes the cycle begun billions of years earlier in a molecular cloud. Gravity gathered matter, fusion converted it into light, and now gravity reclaims it, preparing the ingredients for the next generation of stars. What began as ignition ends as renewal, the universe's continuous exchange between order and change. When the core of a massive star collapses and rebounds, the result is a supernova, one of the most energetic events known in the universe. For a few brief weeks, a single star can shine brighter than an entire galaxy. During this explosion, matter and energy interact on scales that stretch the limits of known physics. What began as a steady source of light becomes an immense wave of transformation, spreading new elements and energy across interstellar space. A core collapse supernova occurs when the inner structure of a massive star can no longer resist gravity. The outer layers fall inward at a speed of thousands of kilometers per second until they strike the dense neutron core formed moments earlier. This sudden collision sends a shockwave outward through the star's body. Neutrinos, tiny, nearly massless particles created during the collapse, carry away enormous energy, and a small fraction of that energy powers the explosion. The temperatures and pressures in this brief event are extraordinary. For a few seconds, the environment inside the star reaches conditions higher than those in its entire lifetime. Atomic nuclei are broken apart, and new ones form through rapid neutron capture, or the R process. This process builds many of the heavy elements that cannot form in normal fusion: gold, platinum, uranium, and dozens of others. Every atom of these elements found on Earth was created in such an explosion long before the solar system existed. After the initial flash, the expanding shell of gas cools and becomes visible as a glowing nebula. Observations of historical supernovae, such as those recorded in the Crab Nebula and in other galaxies, show how the expanding debris continues to radiate for centuries. Shockwaves compress surrounding gas, sometimes triggering the birth of new stars. Even in destruction, The process seeds the next generation of creation. Astronomers classify supernovae into several types based on their spectra and origins. Type 2 supernovae result from core collapse in massive stars, while Type Ia supernovae come from the thermonuclear explosion of a white dwarf that has accumulated too much material from a companion star. Despite their differences, all supernovae mark a sudden, complete release of stored gravitational energy. They are both an end and a beginning, rewriting the composition of galaxies. The light curve of a supernova, its change in brightness over time, tells scientists about the explosion's mechanics. The rapid rise and gradual fade correspond to the expansion and cooling of the ejected material. Elements such as nickel and cobalt produced in the explosion decay radioactively, providing a steady source of luminosity for months. These measurements not only explain stellar death, but also serve as tools for measuring cosmic distances. Type Ia supernovae, with nearly uniform brightness, are among the most reliable standard candles in cosmology. For those observing from Earth, the light of a supernova is both beautiful and humbling. It arrives long after the actual event, carrying the final message of a star that no longer exists. The light that reaches us travels through dust and time, softening as it moves. In that dim glow, the energy of a star's life becomes the quiet illumination of the night sky. As you prepare for rest, consider that the atoms within you, iron, calcium, and carbon, were once part of such an explosion. The matter that forms your body was created in the brief, brilliant moment when a star released everything it had left. Sleep follows a similar rhythm, energy expended, then recovery and renewal. Just as the supernova returns its elements to the galaxy, you return energy to your body through rest. Both are part of the same universal cycle of exhaustion and restoration. The death of a star may seem violent, but in the long view it is an act of continuity. The material scattered by supernovae becomes the foundation for new stars, new planets, and new forms of life. From collapse comes expansion. From silence, new motion. In both the cosmos and within ourselves, endings and rest are only different names for transformation. After a supernova expels most of a star's material, what remains is its dense, compact core. If the original star was massive enough, typically between about 8 and 20 times the mass of the Sun, the remnant becomes a neutron star. It represents one of the most extreme states of matter known in the universe, where atomic nuclei are crushed together so tightly that protons and electrons merge into neutrons. The result is an object smaller than a city, yet more massive than the Sun. The physical properties of a neutron star are extraordinary. A single teaspoon of its material would weigh billions of tons. The density is so high that ordinary matter cannot exist in familiar form. Instead, it becomes a continuous sea of neutrons, held together by gravity and stabilized by neutron degeneracy pressure, a quantum mechanical effect that prevents further collapse. This pressure arises because no two neutrons can occupy the same quantum state, creating an internal resistance that balances gravity even under immense compression. The surface of a neutron star is composed of a thin crust of heavy nuclei and electrons, only a few centimeters thick. Below this crust lies a fluid of superdense neutrons and, possibly, exotic particles such as hyperons or quark matter. Temperatures at formation exceed 100 billion degrees Celsius but decline quickly as the remnant radiates its energy away through neutrinos and electromagnetic radiation. Many neutron stars rotate rapidly, completing hundreds of revolutions per second. These high rotation speeds come from the conservation of angular momentum, the same principle that caused the collapsing cloud to spin faster during star formation. A neutron star's magnetic field is incredibly strong, sometimes 1 trillion times stronger than Earth's. The interaction between this field and the star's rotation produces beams of electromagnetic radiation emitted from its magnetic poles. When these beams sweep past Earth, We observe regular pulses of light and radio waves, leading to the name pulsar. Pulsars serve as some of the most accurate clocks in nature. Their rotation rates are so stable that small changes can be detected with millisecond precision. Astronomers use these signals to test fundamental laws of physics, including general relativity. The discovery of pulsars also confirmed theories about stellar collapse, showing that matter could exist in a state far denser than any known before. The behavior of neutron stars depends on their mass. If the core remnant exceeds roughly 3 times the Sun's mass, not even neutron pressure can resist gravity, and the object collapses further into a black hole. Below that threshold, the neutron star remains stable for billions of years, slowly spinning down as it radiates energy into space. Some neutron stars are found in binary systems, where they pull material from a companion star. The infalling gas forms an accretion disk, heating up and producing X-rays. These systems, known as X-ray binaries, provide laboratories for studying matter under extreme conditions. The study of neutron stars bridges the boundary between astrophysics and nuclear physics. Experiments on Earth cannot replicate the pressures and densities inside these objects, so their observation gives unique insight into how matter behaves when the normal structure of atoms breaks down. Each neutron star is a preserved record of a once-living star's core, frozen in a state that pushes the limits of physical theory. Seen from far away, a neutron star appears small and faint, yet its existence influences everything around it, warping space, emitting radiation, and marking time with precision pulses. It is a heart of pure density, where matter itself becomes rhythm. In that quiet, repetitive signal across space, the universe keeps count of its own endurance, one rotation at a time. If the collapsing core of a dying star exceeds a critical mass, around 3 times the mass of the Sun, no known force can halt its contraction. Not even neutron degeneracy pressure, which stabilizes neutron stars, is strong enough to resist gravity. The result is a black hole, an object so compact that its gravitational pull prevents anything, including light, from escaping once it crosses a specific boundary known as the event horizon. A black hole does not have a solid surface. Instead, it marks a region of space where gravity has become dominant over all other physical forces. The event horizon defines the radius at which the escape velocity equals the speed of light. Beyond that point, all paths curve inward, and no information can return to the outside universe. The core continues collapsing to a point of zero volume and infinite density, a mathematical concept known as a singularity. Around this invisible center, the laws of physics as we know them begin to break down. General relativity describes how mass warps space and time, and inside a black hole this warping becomes extreme. Time slows near the event horizon and would appear to stop entirely to a distant observer. Yet, from the viewpoint of an object falling inward, the crossing happens normally and unnoticeably. This difference in perception shows the relativistic nature of time and space under such intense gravity. Although the interior of a black hole cannot be observed directly, its presence can be detected through its effects on nearby matter. Gas and dust spiraling toward it form a rapidly rotating accretion disk that emits vast amounts of energy as it heats to millions of degrees. These disks are among the brightest X-ray sources in the sky. When black holes draw in material from companion stars, they become powerful X-ray binaries, observable across great distances. At the centers of most galaxies, including our own, reside supermassive black holes containing millions or billions of solar masses. Their formation is still an active area of research. Some likely grew from smaller black holes that accumulated mass over cosmic time, while others may have formed directly from the collapse of massive gas clouds in the early universe. The interaction between these central black holes and surrounding stars regulates the growth and evolution of galaxies themselves. Black holes can also merge. When two orbit each other, they emit gravitational waves, ripples in the fabric of space-time predicted by Einstein and first detected directly in 2015. The detection of these waves confirmed one of the most precise predictions of general relativity and provided new ways to observe cosmic events invisible to light. Each merger releases energy equivalent to several solar masses, converted entirely into gravitational radiation within seconds. Despite their reputation for destruction, black holes play a crucial role in the structure of the universe. They help shape galaxies, influence the formation of stars, and recycle energy and matter through their gravitational interactions. Even the material that crosses the event horizon continues to affect the black hole's spin and mass, adding to the ongoing balance of cosmic systems. For observers on Earth, the concept of a black hole represents both a boundary and an idea, the point beyond which information cannot return, and a reminder of how nature can push the limits of understanding. It is not a void, but a region where known laws transition into unknown ones. At the edge of a black hole, light bends, time stretches, and energy transforms into gravity's pure expression. Every galaxy, every cluster of stars, carries within it these silent engines that shape and regulate the cosmos. They are boundaries not of space, but of knowledge, horizons that mark how far we can see and how much there is still to learn. When a low or medium mass star finishes its red giant phase, it releases its outer layers into space, leaving behind a compact core known as a white dwarf. This object marks one of the quietest yet most enduring stages in stellar evolution. It no longer generates energy through fusion. Instead, it shines with the stored heat left over from its previous activity. A white dwarf is typically about the size of Earth but contains roughly half the mass of the Sun. The matter inside it is compressed into an extremely dense state supported by electron degeneracy pressure, a quantum mechanical effect that arises because electrons cannot occupy the same energy state. This pressure halts the inward pull of gravity and prevents further collapse, establishing a new form of stability. At formation, the surface temperature of a white dwarf can exceed 100,000 degrees Celsius. With no internal energy source, it cools gradually, radiating its residual heat into space over billions of years. The cooling curve follows predictable physical laws, allowing astronomers to use white dwarfs as cosmic chronometers to estimate the ages of star clusters and the galactic disk. The oldest known white dwarfs have surface temperatures of only a few thousand degrees, glowing faintly red or white. The composition of a white dwarf depends on the mass of its parent star. Most are made primarily of carbon and oxygen, the ashes of helium fusion. More massive progenitors can produce oxygen, neon, or even magnesium cores. Surrounding the dense core is a thin atmosphere of hydrogen or helium only a few kilometers deep. Yet this delicate layer determines the star's observable color and spectrum. Despite their small size, white dwarfs possess intense gravity. A pebble dropped onto the surface would hit at thousands of kilometers per second. This gravity also causes gravitational redshift, slightly stretching the wavelengths of emitted light. Observing this shift provides direct tests of general relativity on stellar scales. Some white dwarfs exist in binary systems where they draw material from a companion star. As gas accumulates on the surface, it can ignite in a sudden thermonuclear flash, producing a nova. The explosion does not destroy the white dwarf. It simply expels the accreted material, allowing the cycle to begin again. If the mass transfer continues and the white dwarf exceeds about 1.4 solar masses, the Chandrasekhar limit, it can no longer support itself. The resulting runaway fusion triggers a Type Ia supernova, completely unbinding the star and leaving no remnant. Isolated white dwarfs, however, follow a different path. As they cool, their brightness diminishes steadily. Crystallization occurs in their interiors as ions settle into orderly lattices, releasing latent heat that slows the cooling process. Eventually, After many billions of years, they will fade beyond detectability, becoming theoretical black dwarfs, cold, dark remnants of once bright suns. The universe is not yet old enough for any to exist. From a physical perspective, the white dwarf represents equilibrium achieved through compression rather than fusion. The competing forces of gravity and quantum pressure reach a steady state that can persist for longer than the current age of the universe. It is a kind of endurance that relies not on activity but on restraint. Viewed from Earth, these faint remnants appear as tiny points of pure light, barely visible through telescopes. Yet they embody the resilience of matter itself, a reminder that even after a star's fuel is gone, its structure can remain intact, radiating quiet heat for eons. The white dwarf stage transforms motion into stillness without losing form, showing that stability can emerge not from force but from the precise limits that nature allows. Not all white dwarfs exist in solitude. Many remain gravitationally bound to a companion star, continuing to shape their surroundings through quiet but powerful interactions. These binary systems reveal that even after a star's active life ends, its presence still influences the balance of matter and energy nearby. When a white dwarf orbits a larger companion, gravity can pull material from the outer layers of that star. The gas forms a stream that spirals inward, creating an accretion disk around the compact object. As friction within the disk converts motion into heat, temperatures climb high enough to produce intense ultraviolet and X-ray radiation. The process is invisible to the naked eye but easily detected by modern space observatories. This steady inflow of gas can continue for thousands or millions of years. When enough material accumulates on the white dwarf's surface, the compressed hydrogen layer ignites in a sudden burst of fusion. The result is a nova, a temporary brightening that can increase the system's luminosity by several magnitudes. Once the excess gas is expelled, the white dwarf returns to its former state, beginning the process again. Novae represent not destruction but recycling, a periodic renewal of stored energy. If the mass transfer is unusually high and steady, the white dwarf can grow toward a dangerous threshold. Beyond approximately 1.4 solar masses, known as the Chandrasekhar limit, the internal pressure can no longer resist gravity. The entire star undergoes a runaway thermonuclear reaction, consuming all remaining carbon and oxygen in seconds. This event, a type Ia supernova, releases enough light to outshine an entire galaxy for weeks. Because the physics of the explosion is consistent, these supernovae are used as standard candles to measure cosmic distances and expansion. Binary interactions can also produce more exotic outcomes. In rare cases, two white dwarfs orbit each other closely. Over time, they lose orbital energy through the emission of gravitational waves, spiraling slowly inward. When they finally merge, the result depends on their combined mass. A merger below the Chandrasekhar limit forms a more massive but stable white dwarf. Above it, the system detonates as a supernova. These mergers have been observed both through electromagnetic light and, recently, through gravitational wave detections, confirming predictions made decades earlier. Such systems demonstrate how remnants continue to influence cosmic evolution long after their parent stars have died. They redistribute matter, create new elements, and release radiation that shapes surrounding space. Each event contributes to the ongoing chemical and energetic equilibrium of galaxies. Beyond their physical role, binary remnants also serve as natural laboratories for physics. The extreme densities and orbital speeds involved allow scientists to test gravitational theories under conditions far beyond any achievable on Earth. Measurements of orbital decay in systems like PSR B1913+16, a binary pulsar, matched Einstein's predictions for gravitational wave emission long before these waves were detected directly. Although these phenomena are energetic, the systems themselves are stable in structure and motion. They embody the universe's capacity to sustain order within extremes, steady cycles of accumulation, ignition, and release governed by precise physical laws. What appears as violence from a distance is, in reality, a finely tuned expression of conservation and feedback. If one could observe these binaries in real time, the rhythm would feel almost meditative, matter flowing inward, light flaring outward, then calm returning. The cycle repeats over immense spans of time, maintaining a quiet equilibrium within the vast turbulence of the galaxy. In these repeating echoes of motion and stillness, the remnants of stars continue to remind us that even after collapse, systems can find new forms of stability and purpose. The death of stars does not mark an end, but a renewal of the material from which the universe continually rebuilds itself. When stars shed their outer layers through winds or explosions, they return gas, dust, and heavy elements to interstellar space. This process, known as galactic recycling, connects every stage of stellar evolution into a continuous chain of creation and transformation. The interstellar medium, the vast space between stars, is not empty. It contains hydrogen, helium, and trace amounts of heavier elements such as carbon, oxygen, and iron. These materials are the cumulative products of countless earlier generations of stars. Over time, supernovae and stellar winds enrich this medium, increasing its metallicity. Dust grains form from cooled elements and drift through space, serving as the raw material for new molecular clouds. Inside these clouds, gravity eventually takes hold again. As regions become denser, they collapse to form new stars, each inheriting the chemical fingerprint of the generations before. The carbon in living organisms, the silicon in rocks, and the iron in planetary cores all trace their origins to these earlier stellar cycles. Every atom heavier than helium has passed through a star at least once. Astronomers study this recycling through spectroscopy, measuring the abundance of elements in stars of different ages. Older stars, found in the galactic halo and globular clusters, show low metallicity, meaning they formed when the universe was young and poor in heavy elements. Younger stars in the disk, including the Sun, have higher metallicity because they were born from gas already enriched by prior generations. This gradual enrichment explains the increasing complexity of planetary systems over cosmic time. Supernovae play a central role in this process. Their shockwaves compress nearby gas clouds, triggering new rounds of star formation. The expanding shells also distribute elements across vast distances, mixing material between regions of the galaxy. In this way, destruction becomes a catalyst for renewal. Each new star-forming region carries the physical memory of its predecessors, encoded in its composition. Massive stars, though few in number, contribute disproportionately to this cycle. They live fast, burn brightly, and return most of their material within a few million years. Smaller stars, like the Sun, release their contributions more gradually through gentle stellar winds. Both extremes are necessary. The massive stars provide heavy elements, while smaller stars distribute lighter compounds and long-term stability. The combined effect maintains a balanced flow of matter that keeps galaxies chemically active. Dust particles formed in these processes play subtle but essential roles. They absorb and scatter light, regulate temperatures in molecular clouds, and provide surfaces for chemical reactions that create molecules such as water, methane, and ammonia. These grains also become the seeds of planets. When a new star forms, its surrounding disk of gas and dust begins to clump together, forming the solid foundations of future worlds. Galactic recycling operates over billions of years, weaving individual stellar lives into a coherent whole. The matter expelled from one generation becomes the substance of the next. Every visible galaxy is an ecosystem of this process: birth, transformation, and return, sustained by the physics of gravity and thermodynamics. From a human perspective, this cycle links everything we see and everything we are. The calcium in bones, the oxygen in blood, the carbon in every cell, all originated in long-extinct stars. To exist is to participate in this recycling on a microscopic scale. Each breath, each movement, continues the same exchange of matter and energy that drives the universe itself. When we speak of cosmic renewal, it is not a metaphor. It is the literal reassembly of atoms through the continuous rhythm of collapse and rebirth. Galaxies breathe through this process, their stars exhaling material and drawing it back in again. The universe, in this sense, is not static. It is alive with the constant recycling of its own elements. The universe functions through cycles of activity and calm. Stars form, shine, and eventually release their material, giving way to the next generation. This pattern of energy and rest is not unique to cosmic systems. It appears in all scales of nature, from planetary orbits to biological rhythms. What astronomers describe in galaxies, the human body mirrors each night. Both follow a balance between exertion and restoration. In the life of a star, periods of intense energy release alternate with long intervals of stability. Fusion begins explosively, then settles into a steady rhythm that can last billions of years. Eventually, that rhythm slows as the star cools, ending in stillness. In similar fashion, the brain operates through cycles of wakefulness and sleep, alternating between states of high activity and deep recovery. The physics is different, but the principle is the same. Systems conserve energy through regulated change. When light from distant stars fades at night, the shift in illumination signals the human body to enter rest. The hormone melatonin rises, lowering body temperature and slowing metabolism. Breathing deepens, and the heart rate drops. These biological adjustments echo cosmic ones, where systems stabilize not by constant output, but by strategic quiet. Sleep is the body's equivalent of a star's cooling phase, energy preserved through stillness. The night sky itself reinforces this rhythm. The dim light from stars arrives across space with minimal intensity, providing just enough brightness for orientation but not enough to disrupt rest. For much of human history, this faint starlight was the only illumination after sunset. The brain evolved under this contrast between light and dark, developing patterns of alertness in daylight and calm under the stars. In this way, our most personal rhythms are linked to celestial patterns that have existed since before life began. Astronomers study periodic behavior in stars just as biologists study circadian cycles in humans. Variable stars expand and contract in measurable intervals, their luminosity rising and falling with perfect regularity. The mechanisms differ, stellar pressure waves instead of neurons, but both produce order through repetition. Whether in a pulsating star or a sleeping organism, cycles are nature's method of renewal. In deep sleep, the brain clears metabolic waste, consolidates memory, and resets its electrical patterns. The process resembles the cooling and clearing of stellar matter after fusion ends. Both involve the redistribution of energy toward equilibrium. Sleep, like cosmic rest, is not passive. It is a form of repair that allows continuity. Without it, systems lose coherence and stability. When you close your eyes beneath the stars, you are responding to signals older than humanity itself. The reduction in light intensity triggers changes that restore balance within your body, just as a fading star radiates away its final heat to maintain thermal equilibrium. In that shared principle lies the quiet symmetry between life and the cosmos. Both rely on rest to sustain endurance. As the night deepens, the faint glow from distant suns continues to reach Earth. Those photons began their journey long before you were born and will keep traveling long after you are gone. They carry no intention, yet their steady arrival aligns with the body's own slowing rhythm. Sleep and starlight meet here, where energy becomes calm and perception fades into rest. In the vast scale of the universe, even the most energetic systems find moments of stillness. Stars cool, galaxies pause between bursts of formation, and life itself depends on periods of renewal. Sleep is the echo of that universal rhythm, the small, nightly reflection of the cosmos learning to rest. Every star, whether young or ancient, exists within a larger structure. These immense systems of stars, gas, and dark matter, called galaxies, are the primary building blocks of the observable universe. Understanding how they form, evolve, and maintain stability reveals how individual stellar lives contribute to the grand design of the cosmos. A typical galaxy contains hundreds of billions of stars, along with vast clouds of interstellar gas and dust. The Milky Way, our home galaxy, spans roughly 100,000 light-years in diameter and contains spiral arms filled with regions of ongoing star formation. At its center lies a supermassive black hole, around which the entire structure rotates. Despite its apparent complexity, the galaxy behaves as a balanced system. Gravity draws matter inward, while angular momentum spreads it outward, maintaining a dynamic equilibrium over billions of years. Galaxies come in various shapes and sizes. Spiral galaxies, like the Milky Way and Andromeda, feature rotating disks of stars and gas with curved arms extending from a bright central bulge. Elliptical galaxies are more spherical, composed mostly of older stars and little interstellar gas. Irregular galaxies lack defined structure, often distorted by gravitational interactions with their neighbors. The classification of these forms, originally proposed by Edwin Hubble, continues to guide our understanding of galactic evolution. Star formation within galaxies depends on the availability of cold molecular gas. In the spiral arms of disk galaxies, compression caused by rotation and density waves triggers the collapse of gas clouds. This leads to bursts of new stars, which illuminate the surrounding regions with ultraviolet light. Over time, these young stars exhaust their fuel and return enriched material to the interstellar medium, continuing the cycle of renewal described earlier. Interactions between galaxies play a central role in shaping their structure. When two galaxies pass near each other, tidal forces distort their shapes, drawing out long streams of stars and gas. Some collisions merge them entirely, creating larger systems with new dynamics. These galactic mergers are not destructive in the conventional sense. The distances between individual stars are so vast that few collisions occur. Instead, the gravitational encounter rearranges the orbits of stars and compresses gas, often igniting intense periods of star formation known as starbursts. Dark matter, an invisible component that interacts through gravity but not light, forms the unseen framework around galaxies. Observations of rotational speeds show that visible matter alone cannot account for the gravitational pull holding galaxies together. The presence of this dark halo ensures structural stability, much like an invisible scaffold supporting the luminous disk. Though its composition remains unknown, dark matter accounts for most of a galaxy's total mass and influences the formation of clusters and large-scale cosmic filaments. The long-term evolution of galaxies is a balance between creation and loss. Star formation consumes gas, while stellar winds and supernovae return it. Over cosmic time, this exchange slows, and galaxies grow quieter as their available gas diminishes. Elliptical galaxies represent this final stage, systems where the cycle of birth and death has largely ceased, leaving behind mature stars and faint remnants. From Earth, we see only a small portion of this structure. The Milky Way appears as a pale band of light stretching across the night sky, a cross-section of our galaxy seen from within. Each point of brightness is a separate star, but together they reveal the geometry of the disk that shelters our solar system. The architecture of galaxies demonstrates how gravity, motion, and time cooperate to create enduring forms. No individual star controls this order. Stability emerges from collective motion. The same principles that govern a single star's life extend outward to entire galaxies, uniting the small and the vast through shared laws of physics. The universe itself follows a rhythm of activity and rest on scales far beyond human perception. Just as stars form, shine, and fade, galaxies too experience cycles of motion and stillness. Energy is not constant everywhere. It gathers, disperses, and occasionally pauses in long intervals of equilibrium. Astronomers refer to these intervals as periods of cosmic quiescence, moments when creation slows and balance prevails. In the present era, the universe is relatively calm. Most of the early turbulence, rapid star formation, frequent collisions, and dense clustering has diminished. Galaxies now drift apart, expanding with the fabric of space itself. The rate of expansion increases under the influence of dark energy, an unseen force that accelerates the universe's growth. Despite this motion, the large-scale structure remains remarkably stable. Cosmic filaments of galaxies stretch across space like a web, defining the skeleton of the observable universe. Over immense timescales, this expansion will gradually separate galaxies from one another until their light no longer reaches across the growing void. Star formation will slow as gas supplies are consumed, and existing stars will fade into remnants, white dwarfs, neutron stars, and black holes. The cosmos will enter a long, quiet phase, sometimes called the degenerate era, when only these remnants remain. It is not an end, but a vast cooling period in which energy spreads evenly and activity declines. The idea of a sleeping universe may sound poetic, but it describes a genuine physical trajectory. Thermodynamics predicts that systems evolve toward entropy, the distribution of energy into uniform states. In this distant future, galaxies will no longer blaze with light, but their matter will persist in cooler, slower forms. Even black holes, after inconceivably long periods, will evaporate through Hawking radiation, returning their mass to space as faint heat. If the universe could be observed in that era, it would appear tranquil, filled not with stars but with the quiet glow of residual warmth. Photons would still travel, but their wavelengths would stretch endlessly as space expands, carrying the last traces of motion from an active past. It is the natural rest that follows cosmic exertion, the slowing of processes that once defined structure and brightness. The parallels with biological rest are striking. Just as sleep restores the balance within the body, the universe gradually moves toward a state of even distribution. Temperature differences diminish, motion quiets, and energy becomes uniform. This does not represent failure or decay, but completion, a return to equilibrium after the work of building galaxies, stars, and worlds. For the human mind, contemplating this distant stillness brings perspective. Every night, as you close your eyes, your body rehearses the same pattern the universe will one day follow: a gradual cooling of energy, a reorganization toward balance, and a return to quiet. Your rest is a microcosm of the cosmic rest to come, a reminder that the same physical laws guiding galaxies also govern your heartbeat and breath. In the quiet of sleep, the mind releases its constant fusion of thoughts and reactions. Neural activity slows, memory consolidates, and perception fades into darkness. Yet beneath that stillness, structure remains. The body, like the cosmos, does not cease to exist. It simply redistributes energy, awaiting renewal when balance is restored. When the night deepens and light fades from view, you are aligned with the universe's most enduring rhythm. Everything that exists, stars, planets, and living beings, moves between brightness and calm, energy and rest. In that universal symmetry, sleep becomes more than a human need. It becomes an echo of cosmic order, a nightly reminder that peace is not absence but equilibrium. The universe is not static. The space between galaxies stretches continuously, carrying matter and light along with it. This phenomenon, known as the expansion of the universe, is one of the most profound discoveries in modern science. It means that galaxies are not moving through space in the conventional sense. Rather, space itself is expanding, increasing the distances between all large-scale structures. The first evidence for this expansion came from the observation that light from distant galaxies is redshifted, its wavelengths stretched toward the red end of the spectrum. The farther a galaxy is, the greater this shift appears. This relationship, known as Hubble's law, revealed that the universe is expanding uniformly, with every region receding from every other. The concept overturned the earlier belief in a static cosmos and suggested that the universe had a dynamic origin. The underlying framework for this expansion is Einstein's general theory of relativity, which describes how matter and energy shape space-time itself. In this model, the universe's expansion is governed by the Friedmann equations, derived from Einstein's field equations. These equations predict that the rate of expansion changes over time, depending on the balance between gravitational attraction, matter density, and the mysterious force known as dark energy. Dark energy currently dominates the cosmic balance, causing the expansion to accelerate. Its nature remains unknown. It could be an inherent property of space or an effect of quantum fields, but its influence is measurable through observations of distant supernovae and the cosmic microwave background. As expansion accelerates, galaxies outside our local group move farther away, faster than light can travel, becoming permanently unreachable. Their light, stretched beyond detection, fades into invisibility. This cosmic separation has profound implications for the future. Over billions of years, only the nearest galaxies, those gravitationally bound to the Milky Way, will remain visible. Distant galaxies will drift beyond our cosmic horizon, leaving future observers surrounded by darkness, unaware of the broader universe that once was. The sky itself will change, growing quieter as light loses its strength to the ever-expanding fabric of space. Even now, the expansion influences everything we observe. Photons traveling through space lose energy as their wavelengths stretch, cooling the radiation left over from the early universe. This faint glow, the cosmic microwave background, fills all of space with nearly uniform temperature, acting as a relic of the universe's hot, dense beginning. Its continued cooling reflects the gradual aging of the cosmos as expansion spreads energy thin. On smaller scales, within galaxies, solar systems, and atoms, the expansion has little effect. Gravity and electromagnetic forces remain strong enough to hold matter together. The stretching of space is significant only across immense distances, where the gravitational pull between galaxies becomes too weak to counteract the acceleration. Thus, while galaxies drift apart, the structures within them stay intact. The concept of expanding space challenges intuition. There is no center of the expansion and no edge. Every observer, no matter where they are in the universe, sees distant galaxies moving away in all directions. This uniformity illustrates one of the most fundamental truths in cosmology. The universe has no privileged position. It expands everywhere equally, guided by the same laws that govern every particle and star. From the perspective of time, the expansion is a vast and measured exhalation, a release following the intense compression of the universe's earliest moments. Just as stars radiate their energy and then rest, the cosmos expands as part of its natural equilibrium. It is the universe's own form of balance, outward motion that ensures overall stability, a dynamic calm written into the structure of space itself. Every process in the universe unfolds in one direction, from past to future. This progression defines what physicists call the arrow of time. It is the invisible framework that gives events sequence and memory, allowing change to occur. Although the fundamental laws of physics are nearly symmetric, able to run forward or backward without contradiction, the universe itself clearly prefers one direction. The reason lies in the gradual increase of entropy, or disorder. Entropy measures how energy spreads within a system. A low entropy state is ordered and concentrated, while a high entropy state is diffuse and uniform. In the early universe, matter and energy were tightly compressed, existing in a remarkably ordered condition. As the universe expanded, energy distributed more evenly and entropy increased. This continual increase gives time its direction. The past is the era of lower entropy. The future is where it will always be higher. This principle governs everything from the cooling of stars to the flow of heat in a room. When a hot object cools, energy spreads into its surroundings and cannot spontaneously reconcentrate without additional input. The same rule shapes cosmic evolution. Stars convert hydrogen into heavier elements, releasing light that radiates outward and dissipates. Each transformation adds to the overall entropy of the universe, advancing time's arrow one step further. In biological systems, the arrow of time defines growth, decay, and memory. Living organisms create temporary pockets of order by using energy from their environments, but even this process ultimately contributes to the general trend toward higher entropy. The brain records sequences of events because physical processes, chemical reactions, energy transfers move in one direction. Forgetting, aging, and death all follow the same rule of irreversibility. Astronomers can trace this principle across cosmic scales. The collapse of gas clouds into stars, the fusion reactions within those stars, and the dispersal of their elements through supernovae all obey the same thermodynamic progression. Even the eventual cooling of white dwarfs and neutron stars represents energy spreading toward equilibrium. The arrow of time is not imposed externally, it emerges naturally from the behavior of matter and energy. Time's asymmetry also defines human perception. We remember the past but not the future, because information can be stored only when entropy increases. Each experience leaves a physical imprint in the brain, creating an irreversible pattern of connections. The forward flow of time is thus not only a feature of the universe, but a condition of consciousness. Our awareness of change is tied to the same physics that governs stars and galaxies. In theoretical physics, efforts to understand time's nature often lead back to the second law of thermodynamics. In an isolated system, entropy never decreases. This simple statement explains why a broken cup cannot reassemble itself and why the universe evolves towards states of greater disorder. It also implies that, far in the future, when energy differences vanish, time as we understand it may lose meaning. Without change or contrast, there would be no distinction between moments. The arrow of time connects the smallest and largest scales of existence. It links molecular motion with cosmic expansion, human thought with the evolution of galaxies. Every change, from a spark of fusion in a star to the beat of a heart, follows the same gradient from order to disorder. When you look into the night sky, you see the past, light emitted thousands or millions of years ago. That light's journey, stretching across expanding space, is itself an expression of time's one-way flow. The stars remind us that every shining moment is a conversion of structure into energy, of order into diffusion. Time moves forward not because something pushes it, but because energy, once released, never fully returns. Light is the universe's most enduring messenger. Every photon that escapes from a star carries information about its origin, its journey, and the matter it encounters along the way. Unlike matter, light does not age or decay. It simply travels, preserving the record of events across space and time. Through it, the universe reveals both its past and its constant motion toward change. The light we see today from distant galaxies began its journey when the universe was young. Each photon has crossed billions of kilometers of expanding space, stretched by that expansion into longer wavelengths. What began as ultraviolet or visible light often reaches Earth as faint infrared radiation. The redshift of this light provides astronomers with a direct measure of distance and velocity, turning light itself into a tool for mapping the cosmos. But light is more than a means of observation. It is a physical bridge between matter and energy. When stars fuse hydrogen into helium, part of the mass is converted into photons according to Einstein's equation E equals mc2 E equals mc2 E equals mc2. Those photons radiate outward, warming planets, driving chemical reactions, and shaping climates. Every living organism on Earth depends, directly or indirectly, on the steady release of light from the sun. It defines the boundary between what grows and what fades. The interaction of light with matter allows scientists to decipher the universe's composition. Spectroscopy separates light into its component wavelengths, revealing the fingerprints of atoms and molecules. Through this technique, astronomers identify the elements in distant stars, measure their temperatures, and even determine their rotational speeds. The same principles are used in laboratories on Earth to study everything from interstellar gas to biological cells. Light also records history. When photons scatter through dust clouds or reflect off planetary surfaces, they carry imprints of those interactions. The cosmic microwave background, the oldest light we can observe, preserves a snapshot of the universe when it was less than 400,000 years old. Its nearly uniform glow reveals the density fluctuations that later grew into galaxies and clusters. To study that radiation is to look directly into the universe's childhood. In human terms, light defines experience. It allows perception, guides biological rhythms, and sets the tempo of life. The eye evolved to respond to the wavelengths most abundant from the sun, turning cosmic radiation into color and form. Even the concept of time, as measured by days and seasons, is based on light's presence and absence. Through these cycles, living systems synchronize themselves with the rotation of planets and the motion of stars. Yet light also carries the story of impermanence. Every beam we see is evidence of energy leaving its source, never to return. When light escapes a star, that energy is gone from its core forever. The beauty we observe in starlight is the visible sign of entropy, the steady diffusion of energy that drives the universe toward equilibrium. What gives the cosmos its brilliance is also what ensures its gradual fading. Still, the legacy of light is not loss, but continuity. Each photon that reaches a planet, a cloud, or an observer becomes part of another transformation. It may warm dust into vapor, initiate a chemical reaction, or trigger the signal in a human retina. In every case, light completes its purpose by transferring information and energy forward. When you look upward, the light that meets your eyes is ancient, yet immediate. It began long before you existed, and its journey will continue long after you sleep. In that quiet connection between distant stars and present awareness lies the essence of the universe's memory, written not in words, but in waves of light still crossing the dark. The story of a star is not a single event, but a continuous exchange of energy, matter, and time. From the collapse of gas in a molecular cloud to the quiet fading of a white dwarf, every stage contributes to the universe's long narrative of transformation. The light of a single star may fade, but its material and energy continue elsewhere, shaping new systems, new worlds, and eventually, new life. Nothing in the cosmos is ever truly lost. Each generation of stars inherits the remains of the one before it. Hydrogen forged in the first stars gave rise to helium, carbon, oxygen, and heavier elements that seeded galaxies with complexity. Those elements became the raw material for planets, oceans, and living cells. In this way, the universe recycles its own creation endlessly, maintaining a steady flow from simplicity to structure and back again. The pattern is universal: concentration, release, and renewal. When astronomers study stellar remnants or the light from distant galaxies, they are not only examining history, they are witnessing an ongoing process that still shapes the present. The atoms in the human body, the minerals in mountains, and the air in the atmosphere all carry the same origin story, written in fusion and decay. The universe has been creating, dispersing, and rebuilding itself for nearly 14 billion years, and it continues this rhythm without pause. The continuity of creation also reflects an underlying unity of physical law. The same equations that describe the birth of a star also describe the movement of a falling leaf. Gravity, electromagnetism, and thermodynamics apply everywhere and always. This consistency allows complex systems to emerge and endure. Life itself, dependent on these stable laws, can be seen as an expression of the same universal drive toward balance and transformation. Even apparent endings contribute to this continuity. When stars collapse or explode, their elements become part of future nebulae. When galaxies merge, their stars are redistributed into new forms. On human scales, the same cycle repeats in biology and geology. Matter changes shape, but its essence persists. The cosmos functions through permanence within change, a steady renewal that ensures longevity without repetition. Time, too, participates in this cycle. Every second marks a flow of energy from ordered states to dispersed ones, yet this very flow allows new patterns to arise. Without the release of energy, there could be no motion, no light, and no life. Creation depends on transformation, and transformation depends on the passage of time. What appears as loss is, in fact, exchange, the rebalancing of energy across the universe. When viewed as a whole, the universe resembles a great continuum rather than a collection of isolated events. Each atom, each photon, each gravitational interaction contributes to a seamless fabric of causation. The formation of a single star somewhere in a distant nebula is connected, through energy and time, to the formation of every other. The cosmos is not a machine that runs down, but a system that evolves, always moving toward new configurations of matter and light. As you rest beneath the same stars that powered these transformations, you share in this continuity. The atoms within you once existed in stellar cores, forged by forces that long predate humanity. The light that fades tonight will rise again elsewhere, transformed into new patterns, new warmth, new beginnings. The life of a star is the life of the universe itself, an unbroken thread woven through energy, matter, and memory. It teaches that creation is not a single act but an enduring state, a quiet persistence that sustains everything. In that understanding lies a calm assurance that even as things change, nothing ever truly ends. We, from Sleepy Stories, wish you a good night.